Добрый вечер, каждый. Я надеюсь, что мой разговор будет работать хорошо, как это.
I will hope everyone speaks English enough to, I don't need to do that all night. Okay, thank you everyone for coming out tonight. My name is Craig. I work on the Google Cloud team based in London. I'm originally from New Zealand. This is my second time in Russia. I was in Moscow in 2014, and I'm now in St. Petersburg, and it's much nicer here. So, I work on the team that talks to our customers around our microservices and DevOps software. So Kubernetes is our open source software that we make for people to run in their own environment or for hosted cloud versions. And I'll talk a little bit about a new product that we're working on as well. But I'm not the sales team. I'm an engineer who is trying to get feedback from customers on what they like in our products, what they don't like, what they would use, and so on. And I'm especially interested if anyone wants to talk afterwards. My Twitter handle is there. That's also my email address at google.com. And we'll send these slides around. If anyone wants to take pictures or anything, then there's a hashtag there as well. So I don't talk about writing software. Who here writes software? Okay. Who here takes software other people has written and deploys it or does something with it? All right, so about half and half. So this is the world that I live in, is that other people write code and then we deploy it. So first, this is how I tell how old everybody is. This is called an SD card. This is how we used to deploy software to people. We would write software to a disk and we would copy it out to people, and the more people we wanted to use the software, just the more copies we would make. It was all nice and easy. If you want to give it to lots of people, you just make lots of copies. But then this came along. So the internet, mobile phones. So first of all, you can't fit a disk in a phone. It's just too big. And you can't fold them up. So now we have to distribute our software over the network. So there's two different ways that we do this. We have the model we download applications onto the phone, or we have the normal model we use today of software as a service. So we run the software somewhere else and we distribute the output. The output is normally over HTTP or a protocol built on top of it, like gRPC. And the payload is HTML and images or something in machine format like JSON or protocol buffers or XML if you're in a bad place. But what this means is that the more users that we have for our application, the larger we need our servers to be. So you used to be able to run something on one computer. Everything we do now that has any chance of being interesting or popular runs on more than one machine. And so now we start talking about distributed systems. So going from 0 to 1 machine is hard because you've got to write software and have one instance of it. Going from 1 to 2 is hard because now you've got to worry about state and what happens. So we normally go from 1 to 3 so that we have replicas, and we know that if one of those fails for some reason, then we still have some redundancy. But going from 3 to hundreds should be really easy if you've got everything sorted out. Right? Now the discipline for doing this kind of stuff, the system we use, we have a new buzzword, which is DevOps. So who here is a DevOps? All right, so I find this is really confusing as to what DevOps actually is. So when you search Google for it, you see 8 out of the 10 responses on the front page are, what is DevOps? So that must mean it's confusing. No one knows what it is. It's not well defined. So here's my attempt at defining what DevOps might mean. So we have our first group, we mentioned, are developers, or people who write software. And then we had the old world where we had operators. If we think about those tasks, developers write code. If we're really lucky, they write documentation as well. And then they throw it over this brick wall. We have operations on the other side. And my world here, there's a lot more things that we have to do. here's a quote that I like from an engineer, lady working in California. She has written her own What is DevOps guide, which is on its way to that top 10 list. She says, as a developer, she considered operation skills were like superpowers. Writing code to run in one place on your laptop is really easy. Getting it to run on 3 or 100 machines is a lot harder. And she used the analogy that it's like swimming in an indoor pool to develop on your laptop, but moving to production is like swimming in a river full of piranha fish. So we need to make some changes to the way that our developers work so we can make it easy to do all of those operations tasks. So what are those tasks? Well, we talked about them all before, but now as a team we have one or more applications. We want to do continuous delivery. Who does continuous delivery in the audience? A few hands? So we want to be able to take every time we push a change, we want to be able to build that and then deploy it by our policy. But again, we might be doing that for each application or service on one machine or on many machines. And then we might be delivering to one provider or cloud or multiple providers. So going back to this picture, I don't think this is a good way to think of these two groups. So we don't want to think about making a group in the middle and calling them the DevOps people. But what we want to do is think of establishing a contract between the developers and the operators. So we know if these developers give us something in a certain format, then we as operations people know how to run that at scale. Doing this is like specializing in software. You have your interface, and then you can have a team of people who are able to implement that interface. So at Google, we have teams who are responsible for all of these different layers in the stack. So a team build and run the data centers and run the hardware. On top of that, we have a network team, and they trust that the hardware is always up. If it isn't up, it's this team's problem to sort that out. So now these people can focus on building a reliable network. The next layer up will have a storage team who work on building clusters of storage to run on these multiple machines. And to do that, they need the machines and the network. And they rely on the people in the layer under there. And so these people can become world-class experts at running storage systems and not have to worry about the vagaries of these things because they have a contract with another team that says when things go wrong, they will maintain it. And they will give a system to say, like, we will be up 99.9% of the time. Or they'll set these objectives, which, again, you can read if you're interested in SRE. Google's published a book on site reliability engineering, which talks about how we run these systems at scale. And then we get all the way up to the top. So once you have a service in production, either the developers who wrote the service look after the service, or after a while, we may turn out an SRE team to look after it. Not all services have SRE support, but what that means is once we start off by saying the developers, they are the ones who are going to be paged when there's a problem. And that's a really good way for them to make sure that there are no problems because they don't want to be woken up. Then when that gets good, we hand it over to an SRE team. But they can hand it back as well. They can say, your application is too buggy, or it's not alerting properly, it's sending out wrong messages. So we hand the pager back. So we have this contract between our teams, which basically says the operations team have that power. They can enforce these things and give the pager back, which ultimately gives that trust. And it's hard in some organizations to get to this point. And again, the book talks a little bit about how to get there. It's available for free online if anyone wants to read it. But we talk a lot about what we say breaking up the monolith, of taking a large application and breaking it up into microservices. And it's interesting because they say that an application will look like the company that made it, look like the organization chart of the people in the company. And in this case, you need to be able to have separate teams who manage your applications and different parts of your system if you want to be able to have completely separate microservices. Now, doing this has been great for us because what it has meant is that as we have grown the number of containers that we run or machines that we run, there's another way of thinking about this, then we've been able to do that with only linear growth in our operations team. So it's been 10 times faster growth in the number of jobs we run or containers or machines than our operations team. Now, 3 years ago, we took the ideas from the software that we built at Google internally and released Kubernetes to the world. I think for this audience, I might just take a moment here and talk about some of the systems that we built internally before I go on with the slides. So we started off at Google running infrastructure the same way that everybody else does, which is we had separate machines for all of the tasks that we needed to do, and they were all very important. So we might have started off with 3 machines that were doing the serving of google.com and those 10 blue links that you see for search, and then a pool of maybe 30 machines that were going out and downloading the internet. And this is 1998, the internet's not too big back then. But still, you can't call up Sun and say, hey, give me a computer I can store the whole internet on. So we had to build distributed systems out of these cheap computers to be able to process in parallel all of the data that we downloaded, and then build an index so that these computers over here were able to serve that to people who search for it. Now, we have these machines that are all, they do a task and then they finish and they sort of wait to do something else. But we can't use those machines to run other work on, because when the indexer starts running again, it uses all of the resources and it kicks everything else out, basically. There's no isolation between these jobs. So we have the machines which are doing serving and the machines which are doing batch, and we keep them very separate from each other. So over time, we developed these 2 machines separately. So we have the serving stuff is basically monitored by Python scripts that say, is the serving up? No. Okay, turn it back on again. Just keep it running over and over again. And then we have a work queue system which handles all of the batch stuff. Now, as we think, all right, well, what would it take to be able to merge these 2 things together? We realized that we needed a way of isolating these workloads from one another. So 2 engineers on our team developed what became C groups or control groups, which is a feature of Linux which lets you say this particular process is allowed to use this much resource and nothing more. So if previously we had things like nice and chroot, which are, again, Linux kernel functionality that lets us say use only a certain amount of this resource. Other operating systems, again, those based on Unix, so Solaris and BSD had better control over this space. So for Linux, we came up with the idea of saying, all right, you can set this particular group, which might be 1 or more processors, can only use half a CPU or 100 megabytes of memory or something like that. What that means is we're then able to say, I can run 3 different things on this machine, and I know that if this thing tries to go and ask for more, it's not going to take away from the other jobs that run on there. And then, as we start building out more people start using google.com in 1998, we want to put more machines here. We can start running those tasks on the machines which are otherwise sitting around doing nothing, waiting for the index to be built once a month. And we built a system that let us manage this infrastructure based on top of these primitives. And we open sourced the C groups technology. We gave it upstream to the Linux kernel. And then we stopped talking about it because we thought this system and all of the software that started running inside Google, it was a way to get more efficiency out of machines. So we could take things that previously you'd have leftover space and people would say, oh no, I can't use that. I might need to burst into that eventually. We can actually run work there. And we've made estimates that running a cluster of machines like this has saved us the cost of building a multi-billion-dollar data center. In the paper we published on this technology eventually, we said that if we were to split everything back out again into 2 separate pools of machines for real-time and for batch work, we would need 25% more machines. So effectively for everything we have, we would need to, it's like a 25% saving being able to do it this way. Over time, other people came to Google, saw this technology, and then left. And in the industry, they're like, well, we would like something like that. This is not something that was, again, unique to us, but we were one of the first people with this implementation. And there was a guy who came and worked at Google, and then he went to Twitter. And he said, well, hey, I'd very much like something like that. And he looked around to see what there was. And there was an open source project running out of an American university called Mesos. which was, again, a scheduling system for doing batch workloads. So he talked to the guy who built that, who then eventually went to work at Twitter as well, and they built a system based on this. And then eventually, we published a paper talking about a second generation scheduling system that we were using. But we kept the very first one. Even the name was very secret. The system was, we call it Borg, which is, again, it's a Star Trek joke for anyone who's both old enough and has seen American TV to understand. New people coming to Google have no idea what that means anyway, but we don't talk about it too much because Paramount owned the copyright on that name and so on. So this system, people started doing implementations of it outside. And as we started becoming a cloud provider of our own and wanting to sell access to things and get into this market, we realized that some of the ideas that we had published in the past had been parallel implementations had happened. So at Google, we'd invented the system for chopping up and indexing the internet, a system called MapReduce. And then a guy at Yahoo had taken this and had built a Java implementation, which is called Hadoop. And it was divergent from what we were doing internally. And we wanted it to be that the ideas of containers and scheduling had come about in the community, that over time Docker had come about and taken the open source work from Google and the work that had come afterwards and things like LXC and built tooling around running these container processes. And we wanted to work with the things people were used to, but not just say, here's a paper on how to do it and let someone else drive that, but we actually wanted to say, here's an implementation that we think works very well. So we released Kubernetes. What is Kubernetes? It's container-centric infrastructure for deploying and managing applications. Well, there's a lot of big words there, and let's see what we mean by those things. What is a container? So I think a container is only actually two things. It's an application bundle, so it's software like an RPM or a tar or a zip file, a way to package up that software together, and then a way, as I mentioned before, to run that software on an operating system directly on top of a kernel, so you don't depend on other software that's on the machine. You package up all of the libraries that you need inside that bundle, and then you can run it on this machine with those restrictions. So you can say what it is allowed to use in a way that means you can trust to put multiple containers on a single computer. A lot of people will have been using virtual machines to solve the similar problem. The difference between a container and a virtual machine is kind of like the difference between starting an app on your phone and rebooting the phone itself. So to start a phone from scratch or boot up a computer, it takes about 45 to 60 seconds. And then all of the data is mixed up in the same image. So when you make changes to applications, they're written into the same image. You can't roll back to, when you upgrade your phone, you can't only roll back to the previous version. A container is like an application running on your phone. So you tap on an app, it takes about 200 milliseconds to start an app normally. And the thing you download has everything it needs in the app, and then the data is stored somewhere else. So even if you delete the app and then reinstall it again, you have access to your data because it's not stored in that container bundle. So I mentioned containers were associated with Docker. Docker was this French company called .cloud who built a platform as a service, and they built some tooling around the Linux infrastructure to make it easier to run workloads. It turned out that the tooling was more interesting than the platform, and so they pivoted their company in the direction of that tooling. They are not the only people who have built container infrastructure. So CoreOS had worked on some software called Rocket, which was meant to be a specification for how a container system might work and an implementation of it. The thing called AppC was their spec, Rocket was the installation. So when someone came on and said, here's something else we want to do, we worked with people like Docker and said, all right, we want to bring these things back together. So now we have a standard. We have a thing called the OCI, or the Open Container Initiative. And that's a standard format for both the runtime and the image. So two different standards for packaging up software and then running a version of that at any given time. So Kubernetes runs containers on a fleet of machines. It doesn't deal directly with containers. but it actually deals with this thing called a pod, which came out again of the systems that we ran in Google, saying we quite often see work that we need to join together. So you might have a container which serves files, it runs a web server, but then you also have a container which sends information out to logs, or it takes incoming traffic and checks it or something like that. So these things need to, every time you have one, you have the other together, like the software you might install on a virtual machine. If they're not built by the same people or they have the same life cycle, we put them in separate containers, but we run them together tightly coupled in the same pod. Pods have an IP address, and so everything in that container you can just talk to the other container by connecting to localhost on whatever port your container runs on. Now, Kubernetes works as the distributed system where you specify what it is that you want. You give a declaration saying, I want 10 copies of this service running somewhere. You don't say, I want it running on that one, and this one, because you're a person and you shouldn't be thinking about that. There's a machine that can think about that for you. So you just say, I want 100 megabytes limit for this thing, and I want 10 copies running. And the Kubernetes master looks at all of the machines in your cluster and says, I've got space here and here and here, or I'm out of space and I can't do that. And it will also look over time at the changing state of your cluster based on other things. Like if you unplug a computer, you've now got all of the things that were running on that machine aren't running anymore. So if you asked for 10 and now you only have 8 running because 2 were on the computer that you unplugged, Kubernetes will notice and it will say, hey, you wanted 10, but you only have 8. So it will find 2 more places and it will start 2 more copies of that running somewhere in your cluster. That's a thing called a replica set. Now, because we're running in this dynamic environment where we don't know where work is when we start it up, we need a way of grouping together these pods that are all doing the same thing, that work together in some fashion. So a service is a way of saying all of those 10 things, we're going to group them together, give that service an IP address, and now if I want to connect to any one of those replicas, I can connect to that IP address and I'll be forwarded to one of them based on where they're running. So again, they will come and go over time, they'll get different IP addresses, but the IP address or the name of the service will be stable over its life cycle. That's another learning from Borg. With Borg, you have to call out to a naming service. You have to rewrite your application and say, be aware of the fact that I'm running in a cluster, call out to the service, ask these for a list of places it's running, and then go through it yourself. So Kubernetes automates that for you so you don't have to build that into your application. As a developer, you shouldn't have to change your app at all if you're going to run in this kind of environment. So here's a description of what you want to run. So you might want to run a pod. Its name is Redis Django. And so as you might imagine, there are 2 containers inside here, one with the Redis image running on this port, and one with the Django image running on port 8000. So in your Django code, to connect to your local Redis instance, you just say, open a connection to localhost :6379, and then you'll connect to your local running instance of Redis. And every Django instance will have a corresponding Redis instance. We haven't said which server we want to run this on. Kubernetes figures that out for us. Kubernetes does a lot of things for you. So it handles scheduling. You say, here are my 10 things. It finds where to run them. It looks after life cycle and health. So again, if things come and go, or if services are unhealthy, you can define an endpoint to say, this is only up if it returns an HTTP 200 to a certain endpoint. And if not, then kill it and start new ones and so on. You can automatically scale. So you can say, in the event that the average CPU usage of this group goes over a certain number, add more replicas until it comes back down again. Or you can attach an external queue and say, in the event that some external thing goes over a certain point, so you might be processing a batch queue of some sort, when the queue gets bigger, turn on more workers till the queue gets smaller again. Mention naming and discovery. So your front-end service can just say connect to back-end. It doesn't need to know how many replicas are running or anything like that. It just connects for you. It handles the load balancing. It abstracts away storage. So you say, I want a 100 gigabyte disk. on Google, that's a thing called a persistent disk. On your data center, it could be an iSCSI volume. But Kubernetes lets you define a difference, so you can take the same instruction manifest file and run that on either place, and your storage administrator just says, here's how to plug in your storage from your backend. And it can be defined automatically, so you can just say, if I need 100 gigabytes, it can be automatically provisioned on a cloud where you have that, or you might need that to come in from your administrator if you have to assign disks. Now, when we're dealing with distributed systems, we can't worry now about the state of any one container, because they can come and go, and that's perfectly natural. So we need to do logging and monitoring outside of our runtime environment. So all of the logs from containers can be sent off to an external endpoint. Same with monitoring information. So we have built-in primitives to take the logs, export them somewhere else, and then you need to look at the logs for all of your containers as a whole to figure out what the state of your service is. Same with debugging and introspection. You need to be able to look into the state of something while it's running, but then you've gone and changed that container if you've logged into it. So you might want to kill that and then have a replica set start a new one. Obviously, we want this to be secure, so only people with access are able to log in and do various things inside your cluster. And that's what we think of as piranha-proof infrastructure. So now, as a developer, you're going to write your application, package it up in a Docker container, and give us a manifest file on how to deploy it. You give that to Kubernetes, and you don't think about anything more. Kubernetes will think about the hardware, physical or virtual, underneath, and it has its own contract as to how it interfaces with those people. But you, as the developer, don't worry about it. So developers, we like you to think of this as a simple, fast, and fully managed way to run containerized applications from test to production. There's a marketing quote you don't need to read, but for these guys, it let them cut the time to deploy their application so that now they can deploy to production in less than 10 minutes, and then they can go 30 or 40, 50 times a day. There's a big American ticketing company called Ticketmaster, and they estimate that it costs them $60 to $90 million a year just to deploy code, and then if it fails, to roll it back and so on. So having APIs and a system which means we can roll these things out, and because these are self-contained images, if we need to roll back, we just terminate that process and restart the old one, and those files are still on the disk, so it's very easy to safely roll out and roll back. For the operators who are looking at running software on their hardware so that developers can run on that, it's a standard platform for reliable and scalable clusters without operational overhead. Have we had any business people sneak into the audience while no one was looking? So for what I tell CTOs when I talk to them is that Kubernetes enables interoperability and it removes vendor lock-in. So these containers can run on any Linux kernel, and Kubernetes can run on any environment. There are now containers for running on Windows VMs as well. If you have a Windows application, you can run it in a Windows container. And there's work going on through beta and eventually GA in Kubernetes for running Windows workloads as well. I mentioned there it's consistent, so you can run the same software on-premise, on the cloud, or in a hybrid that runs between them. You can hide the differences between those environments from the developers as an ops person. So at Pokey, they said that Kubernetes did nudge them in the direction of running on Google Cloud, but they're more agnostic than ever because Kubernetes can run anywhere. A lot of people want to use things like Terraform or like Kubernetes to build portable software, not because they think that they want to move and they want to say, all right, today these guys are 2% cheaper, so we're going to move it over there. But to know that they're not locked in, that in the future, if they get a good deal or if they need to move, or some cases like when the law changed a couple of years ago about data being stored in Russia, it's like if you need to move out of a cloud and move locally, this would be a platform that would enable you to do that. Here are a bunch of companies who are running Kubernetes, and some of them running in clouds and some of them running on-premise. So I'm going to talk a little bit now about applications written for cloud. So we launched Google App Engine in 2008, which was one of the first platform as a service. After that, another early PaaS was Heroku, and the co-founder of Heroku published the 12-factor manifesto. Everyone seen this before? A few nods. So this is sort of saying, here are some of the best practices for writing these software as a service applications on a modern platform for serving potentially billions of users. We went a bit further when we released Kubernetes, and we said, here's our concept of what we think to write an application to run on clouds natively, a cloud-native application. This took best practices from how we've run our applications internally at Google, and also from things like 12-factor and how the community have run. So we think a cloud-native application is container packaged, so you get that predictable copy file deployment and the resource isolation. It's dynamically scheduled, so again, you can get higher efficiency because a machine is making decisions on where things should run, and that cuts down your operations cost. And then it's microservices oriented. So each of these applications can be written in a different language. You don't have to have a single environment for everything that you run. And they can all have different life cycles. You can upgrade this part 10 times quicker than that one if you want. So because these containers can run anywhere, we wanted to make sure that the software that we built was used by everybody, not just a Google thing that people would only come to us to run. So the first thing we did when we got to 1.0 is we created a group. So this is a project as part of the Linux Foundation. And we gave them the copyright, the ownership of the code, the trademarks, and everything. So we set this group up to steward Kubernetes and other projects that work in cloud native. Before we went GA, Google was the largest contributor, but there was a lot of early people like Red Hat, for example, involved. Over time, we saw everyone else pick things up. So even though these things are shown the same size, Google's now doing a lot more work than we were back then, but so is everybody else. So our proportion has actually gone under 50% recently. Here are a few of the people who are working on Kubernetes. So I'm not sure, Marantis, I think they're a Russian company. There are a couple of people around the world, so Alibaba here, I'm not sure again about other companies local to you. But a lot of people, a lot of companies here, including all of the big cloud vendors worldwide. Obviously, this is not necessarily all of the world, I'm not too sure about the Russian market. But this is a great group of people, like there's no other trade group that I'm aware of that has all of these members participating. And these are the platinum members, some of the new ones here, who are paying a lot of money to be a member of this group. And that's them saying, look, we are committed to this. We think this is something that our users are going to want to run in these cloud environments. Again, a couple of marketing things I'll pick over. So a couple of companies, Pivotal, I mentioned here, they are running on-premise. So there are now corporate vendors you can buy if you want to run Kubernetes on-premise, but you can, of course, just download it and run it, the open source pieces. Kubernetes can run as a framework on top of the Mesos system. And I haven't updated these slides since last week, but Docker themselves actually announced that they're now supporting Kubernetes as container platform. Now, Pivotal described Kubernetes as dial tone of the internet. So it used to be you'd pick up your phone, you'd get the noise to say, yes, that the phone's working. But when you pick the phone up, you think, well, it means I have a cable from my house to the box at the end of the street, and that's working. There's a box to the end of the street that's connected back to the telephone exchange, and that's working. And millions of dollars or rubles of equipment running on the telephone exchange is working so that I can make a call to anywhere in the world. But you don't pay for any of that. You just pay a small monthly phone bill, and that gives you access to all of this. So we have a managed service for this at Google Cloud. I'll skip over it very briefly, but it's called the Google Container Engine. It's a fully managed Kubernetes environment, so we handle all the things like backup and monitoring and restarts and everything, offer an SLA, and we also manage the components that run on the nodes so that you can just focus on the square part there that has your workload run to it. So we do things like manage, update Kubernetes versions and node operating system and everything, repair broken nodes, give you a nice UI for it as well. Again, people using open source, there is a built-in Kubernetes UI and a lot of platforms that can run on top of this. And a nice audit log of everything there. So here's a few of the companies that are running Google Container Engine. Okay. So I'm going to give a 2-second sneak peek of some new stuff we're working on. Did anyone see my talk at DevOps last week? I gave a talk on this, but I'm just going to briefly introduce it. When you move to these distributed systems, now we have different microservices. It's very hard to monitor and know what's going on all across this environment. So we've invented this, the community people, not just Google here, they've invented this concept of a service mesh. So think about, like, instead of the network worrying about MAC addresses and bytes and things on the wire, wouldn't it be great if we could say, I'm going to worry about the communication between services. I want all of these things, which could be running again anywhere on my physical network. I want to be able to say, this service can access that one, but not this one. Or I want to be able to rate limit traffic between this service and that one. Or allow only rate limited traffic in from the internet to my service. So you could do things like improve reliability through routing, and then it can also, because it knows the status of traffic between your services, it can do things like do monitoring and introspection of services for you across everything running in your distributed system. So how a service mesh is generally implemented is with a proxy server, a thing called a sidecar. We talked before about how you can have a pod with multiple containers running in it. So you write the service here, which runs in your container, in your pod, and then we plumb in a proxy server, which can get rules programmed into it. So you can have these sidecars programmed with SSL certificates, TLS certificates, so that all traffic between all of the services in your cluster must be authenticated. And then you can do rate limiting and control and all of those things. So once we have this network or this mesh of these proxy servers, we're able to program in the rules and then also use them as a point to get this visibility. So we have a new open source project built with teams at IBM and Lyft, which is called Istio. Istio is a framework for connecting, securing, managing, and monitoring microservices for things running inside Kubernetes, but also for legacy services, for things running on VMs. And we also want to see this extended to working with people like Cloud Foundry and Mesos as well, and first-party providers, people who run physical things, how we can build them in as well. So just a few of the things that you can do here. So with the connection, because we now have interjected between the network connections, we can say, all right, well, we know that this route, this particular service, maybe its cache is cold, it doesn't respond as quickly, so we can say, don't route traffic to there, route to somewhere else. Or we can say, in case of traffic control, we can say 10% of the requests from iOS devices go to this service rather than that one. So we can do canary deployments and we can do traffic routing without needing to change the number of backends that we run like we do today. These services are also able to send metrics up to a central service. So just by installing this on the cluster, you're able to get visibility into what's going on in your network, aggregate numbers of service successes and failures and so on. And you're also able to do distributed tracing. So if a call from a user calls multiple microservices, you can look and say, well, this is how long it took for each step in that chain. And as I mentioned, you can do end-to-end authentication and authorization and make sure that all the connections between things. So if somebody was able to break into one of these containers, then their only path out to other applications is through the secure network. So they're not able to connect to things that they shouldn't be able to. So that's something that we're sort of a 0.2 release of that at the moment. Over time, we will expect a 0.3 at the end of this year, which we say is sort of production ready, but still got a lot more work to do. And it should be sort of 1.0 mid next year. But if you're interested in any of these projects, so Kubernetes.io is the website for the Kubernetes project. Container Engine, cloud.google.com/container engine. And Arthur mentioned that we've got some codes for Google credit for people who are interested in getting started there. And then Istio is a new project at istio.io. So thank you very much, first of all. Do you have time for a couple of questions, or anyone want to ask anything?
Okay, thank you, Craig. I missed one thing, that we have promo codes for Google Cloud Platform, about $200 or $300, quite a lot. And first question from me, what we can do with this money with Google Cloud Platform, not exactly with Kubernetes.
Sorry, what can you do with
$200?
All right, so I mean, running a VM costs a small number of cents per hour. So like you can probably start a Kubernetes cluster and run it for a couple of months for that price. So the the fee for running a container engine cluster, it's free for under 5 nodes for the management fee, but then you just pay for the use of the VMs and the disks and everything that you use. So for people who aren't familiar with Google Cloud, all of the same things you'd expect in terms of other clouds you've used, so access to virtual machines and disks and processing sort of storage and infrastructure pieces, but also some very interesting big data services like the things we've talked about that we use internally. We give versions of them available externally as well.
Thank you. That's not bad. And we will give you promo codes for your questions. Not a big deal. So, any questions? Okay.
If you're shy, I will also take questions by email or Twitter afterwards.
If you have problem with English, you can say it to me and I can translate it. Probably.
Hello. My English is bad.
So my Russian is worse.
I'm not sure.
Okay.
So what's about kernel settings per different apps? So some apps wants some specific kernel values, and how I set it in Kubernetes. For example, transparent huge pages, or maybe some networks buffers.
Right. So the container abstraction uses namespaces inside the system, and some of those settings can be set differently in different namespaces. So you can say your kernel namespace for your container is different for the maximum number of TCP connections or something like that. For things like huge pages, you can run, there's a thing called a daemon set, which is a way of saying to Kubernetes, take this software and this container or this script and run it on every node in my cluster. So for Kubernetes, if you need to enable something like transparent huge pages, you can say on every machine, run the script which will set the settings for that. But again, if you have two things that need different kernel settings, you might or might not be able to run them on the same machine, depending on if the settings are namespaced or not. So down the back, there's a gentleman who might have more of an answer on that.
Hello.
Hello.
I have a question about. I will be on DevOps, and I hear you said Docker is not good service, but I want to one question about Docker with console. It's work like Kubernetes cluster because it's load balancer UI for devs. Why I need to use Kubernetes or not console?
So if you think back to the picture with developers on one side and operators on the other, Docker came from the developer side. So they're like, how do we make it easy for people who write applications? And Google came at the, we have to make it hard for those people to make it easy to run at big scale. So we say there are things that developers cannot do because we know that we cannot run that. If you write a bad application with uses huge amounts of resource, we cannot run that on 100,000 machines all at once. So Docker has been working, sort of edging towards our system. So the very first versions of Docker Swarm and so on were saying, right, we're going to try baby steps and very small systems. So their thing worked fine if you have 5 computers, but if you have 5,000, it wouldn't work. And Kubernetes was very hard to get going with, but it would work with those things. And the same with Mesos. So Mesos, you can run very big clusters, but you have to change how you run things. So because all of these things are open source, we think they're all, like, Docker is getting better at operations and Kubernetes is getting better at development. So they are coming together. But because the community around Kubernetes, there's so many people who are interested in helping build it, we think it's the second most successful open source project of all time behind the Linux kernel, just looking at the speed of development and the number of contributions and so on. So Docker, say, people are asking for Kubernetes. You can run, again, especially if you have just one computer, you can run Docker on that. If you have a small number, you can things like Docker and console and so on. But we think that the patterns here are really good for when you get to a very big scale. So if you're able to use them in your smaller clusters as well, then if you get lots of people want to use your app all of a sudden, it's very easy to move to the big scale.
Hello.
Hello.
Thank you for your speech. I have a question. How Kubernetes manages when one of the node fails completely? So it goes down, and what happens to containers running inside this node? Does Kubernetes rearrange them to another node, or how it would handle such fail?
Yes. So Kubernetes cares about the containers that run on the node. So if you have, let's say you had 4 nodes, and they had 2 containers each because you asked for 8. It happens. Like it doesn't have to be that way, but that's what it ended up. If one node goes away, Kubernetes says, I only have 6 now, and then it will look for space on the 3 remaining nodes to put them on. There is also an add-on for auto-scaling a cluster. So if you're running in a cloud that you can get new computers automatically, if you cannot schedule because your machines are full, then it can send a signal so that your autoscaler can add new machines. But if your 4 machines were 4 computers in front of you, and then one of them failed, like it obviously can't add any more. So Kubernetes does not manage the machines. It relies on the cloud or the operating system vendor underneath to do that, but it will look after the workloads on top. And there are lots of settings that can say, well, if the machine fails, but it might come back within 5 minutes, it can say, well, wait and see. You can define for each workload how long to wait, like to see whether it terminated.
Okay, thanks. And the second question, how then it handles some persistence state, some stateful application when node goes down,
Yes.
and we have state on this node, what happens, or how Kubernetes handles this?
So we had talked about like a thing called a replica set. So it has just stateless applications. It just makes copies and copies and copies. The best thing to do is when you have network attached storage. So we have a thing called a stateful set, where you have an application and a network disk, and these things are kept together. So if this node goes down, it reattaches them to somewhere else. We're also now being able to manage local storage volumes. So Kubernetes can say, I've got stuff on this machine. If that machine goes down and has local data, then obviously it can't access that anymore. But you build your application out of replicas. So you might have, again, your 4 nodes each have half of the data on them. So this node goes down. Your 3 remaining nodes have enough to keep serving all of the data. And then when you add a 4th node, then things like Cassandra or MongoDB or something, they know it can join the ring and it can start replicating the data until it has a full copy again. Yeah, so Kubernetes works with applications that know how to run in a distributed environment. If they don't know how to run in a distributed environment, so if they're older applications, they need that data, then either you have to wait till that computer comes back again, or you need to have the data stored separately.
Okay, thank you. And we have one more question.
I'll take 2 more because there's one right there.
We have only one promo code more.
Oh,
no, okay.
It has to be a free question.
We have enough.
Okay, thank you. What you can say about open source load balancers for Kubernetes?
Okay, so the Istio project I talked about uses a open source load balancer called Envoy, ENVOY. It was written by Lyft for their microservices infrastructure. It's written in modern C++, and it's very extensible. You can reload things without having to restart the application and so on. The Istio ingress uses Envoy to be able to handle load balancing. And again, you can use that to do anything inside. So that is my recommendation if you want to run your own load balancer. In cloud environments, you can interact with the cloud's internal or external load balancer. And then there's Nginx and HA proxy integrations and all those kind of things. But Envoy is where we're heading in terms of the one I'd recommend.
Thank you. And finally, the last question.
Thank you for your speech. Could you please describe?
I suppose you describe that our infrastructure should be like code. So my question is how we have to test our infrastructure and don't spend a lot of money. Maybe Minikube or something like this. Any patterns?
Yes, so gentleman mentioned Minikube, which is a way of being able to run a little VM on your own machine that gets started with Kubernetes. It is possible to run the Kubernetes. So the Kubernetes components just come in containers that you can run anywhere. So the way that Docker's integration is working, we'll be using their own local VMs, so their Linux kit environment. Like if you download Docker for your computer today, they will support running Kubernetes clusters on top of that. It is possible, like Minikube is just one VM, so everything you deploy will end up on that node. So if you want to test what happens when you have multiple nodes, then you need multiple VMs. You can do things like VirtualBox or Vagrant or so on in your own environment. You can run on physical machines. I have a colleague who has Raspberry Pis. He sets them up and does a little demo with that. But again, like you can, especially if you want to run for a short time, you can start up a cluster on the cloud, 10 machines, run whatever test you want, and then turn it off again. It doesn't cost too much. What do I think about Terraform? Terraform is great at managing old-fashioned infrastructure, so virtual machines and so on. I was talking with a gentleman who was at the conference last week who works on Terraform. Terraform has an option to, you can use Terraform to get Kubernetes onto the servers. Kubernetes doesn't have an opinion about how it gets deployed. So you can, again, there are many tools. There's one called KOPS, K-O-P-S, which uses Terraform to get Kubernetes running on the actual machines or the VMs. It is possible, but not recommended to use Terraform to deploy container workloads on top of Kubernetes. And the reason is because Kubernetes can change the workloads. Like when you submit work, it can say, automatically install those sidecars for Istio, for example. And then Terraform says, that's not what I asked, and then it keeps trying to change it again. But it is possible to, like, if you want to use that for everything, it's there, and we're working with HashiCorp on making that better.
Thank you.
Thank you very much.